Hello guys, welcome to video 2, and in this video we'll be discussing the motivation, or more specifically, the difference between analyzation done in the quantitative finance field with respect um, to other disciplines of finance. And to demonstrate this, I will be starting with an analogy. So I want you guys to consider a dropping ball. Now, when we talk about a dropping ball, we're obviously interested in the movement of this ball. And the movement is obviously with respect to time, right? With every position of time, we're going to have a different um, index of where the ball is at that moment of time. So I can represent this as such. I can create a table of t and x of t, where t is the independent variable and x of t is the dependent variable. And let's say my time goes from time equals 0, 1, 2, 3, and so on and so forth. Now, let's say before I drop the ball, my initial height that the ball is at 100, let's say, meters. And then at time equals 1, this goes down to 90. Time 2 goes down to 70, 40, and so on and so forth. Now, if I had a different ball, let's say with a different gravitational constant and other constants that are relevant which vary from this specific ball, let's say this is x of t1, we'll construct another table. In the same exact structure, but this is going to be our second ball. I'll denote that as x of t2, and my independent variables are going to be the same. And let's say this ball starts off at 100, or maybe not 100. Let's change that. Let's start it with 90. And then let's say it goes down to 70 after that at time equals 2. It goes down to 25, and then at time equals 3, it goes down to 5. So on and so forth. Cool. Now that we've done that, we can discuss the other part of this analogy, which is going to be a financial asset, or a stock price. And how can I represent this? Well, I can represent it in the same exact way. Let's say I have a table of my independent variable time and my stock price as a function of time, and let's call this S of t1. And this can be any stock you so choose, right? But the movement, right, we can say in increments from 0, 1, 2, 3, and we can say this increment is in terms of days, for example. You can change that increment if you so wish, right? But just for representation purposes, right? Let's say our stock price starts at 200 on the day we choose to start analyzing it, and then maybe the next day it goes up to 203. And then on day 2 it goes down to 198, and then day 3 it goes up to 201, so on and so forth. And in the same way, I can represent another stock with the same exact table. Let's call this S of t2. Now this stock could probably start at 100, goes up to 103, goes further up to 105, and then goes up to 108, for example. So in the way we can represent a dropping ball, we can also represent a financial asset, as can be seen. Now, there's an issue with this, a very clear issue. And let's go back to the dropping ball example. If I wanted to analyze an n number of dropping balls, I would need an n number of tables. But with what we learned in physics, if you've taken physics, we can represent pretty much every dropping ball as a kinematic equation. And this looks as such. So we'll have x of t, and this is a function of time, and we're going to start with our initial position, add that with our initial velocity, scaled by time. I'm going to add that to our acceleration, which is scaled by 1/2 a naught t squared. Now using this equation, I can choose my x naught, v naught, and a naught to calibrate any system I so desire to analyze. So if I were to do a graphical representation of this, let's only do the positive axis because in terms of a dropping ball, that's the only axis that so makes sense. So if I have t, and if this is my x of t, and let's say we have an n number of balls, my first path of some ball could look like this. Now, if I were to throw the ball, right, with some initial downwards velocity, I would probably get a function something like this. Maybe if I were to change the gravitational constant, I'd get something like this. And these all represent different balls. So this could be x of t1, this could be x of t2, and this could be x of t3. And I can repeat this process with different constants x naught, v naught, and a naught to represent an n number of balls. Now, something else that I can do with this is further analytics. For example, I can find my derivative of my position function with respect to time, which will give me my velocity as a function of time. And I can also find my second derivative with respect to position, which is just going to be equal my first derivative with respect to velocity over time, which will give me my acceleration as a function of time. Now, generally with dropping balls, a of t is going to be constant. But depending on how complex the system that you want to analyze is, it does not need to be. So what have we concluded? Well, there's many ways to represent a dropping ball, and one way is a table as such. But there's a better way. We can represent it as a kinematic equation, and with a kinematic equation, we can represent an n number of balls and also do further analysis on variables such as velocity and acceleration. Now, to go back to the stock example, it would be very nice if we had, let's say, in the same way we have a kinematic equation, if we had a financial asset equation such that I can analyze s of t1, s of t2, all the way up to s of tn, all with one equation. So can I do this? And that's the question we'll be answering. Now, to get you guys to start thinking about how to do this, I will draw out a few financial assets. And obviously financial assets can't go negative either. And let's say this is going to be my starting time and the time axis, and this is going to be my stock price as a function of time. Now, I could start a stock here. This could be one sample path for the stock I so choose to analyze. Another one could be something like this. And so on and so forth. So this could be my S of T1, S of T2, S of T3, and obviously I can have many more going up to S of Tn. So going back to the question, we want to find one equation with parameters that we can choose, such as x naught, b naught, and a naught, to calibrate and represent all of these stock prices. And in the next video, we'll be discussing how we can go about doing that.